I'd like to do today is to talk about magnetic moments, and we introduced the idea of a magnetic moment in a previous lecture, but now I want to take a deeper look and then show you where the source of attraction and repulsion between magnets comes from using this argument of magnetic moments. So just a quick recap, we talked about the magnetic moment for a current loop last time. But as discussed in a previous lecture, the magnetic field lines for a current loop look very, very similar to the magnetic field lines for a bar magnet. So this similarity allows us to draw the following conclusion, that current loops and bar magnets both have these magnetic moments. So remember that in the lecture on magnetic moments, we said that the magnetic moment points in the direction of the field at the center of the loop. So if you take your right hand and for a current loop you curl the fingers of your right hand in the direction of the current flow, your thumb gives the direction of the magnetic moment for that, which is the same as the direction of the field at the center of the loop. It's basically the north pole of the bar magnet shown here at the right. And so current loops and bar magnets both have these similar field lines, and that gives rise to a magnetic moment, and the magnetic moment points in the direction of the north end of the magnet as shown here. Now, as discussed, both of these objects, current loops, permanent magnets, these dipole moments cause them to want to align in the presence of an external magnetic field. So if you have a constant magnetic field, for example, then your current loop will feel a torque in the presence of that external magnetic field, and it will want to align so that magnetic moment points in the direction of the magnetic field. Now, that's one phenomenon that we're all used to in bar magnets. For example, if you've ever held a compass, then you know that when you put the compass in the presence of the Earth's field, the little bar magnet, which is the compass needle, will rotate to point towards the north, right? So magnetic dipoles will also rotate in the presence of the field. And we also can see that magnetic dipoles, if you have two bar magnets, for example, and you try to push them together or pull them apart, the north or south-south will cause a repulsion between the magnets, so you'll feel a repulsive force. But opposite poles, north-south, they attract one another. So I'd like to talk about the source of that attraction today. So let's talk first, to lead into this argument, about the magnetic field for a current loop along the axis of the loop. Okay, so we discussed the magnetic field for current loops in a previous lecture, and if you get off the center of the current loop far away, well, relatively far away from the axis or from the center of that loop along the axis that runs through the loop, right, then you can find the magnetic field. Now, this I'm not going to spend a lot of time on. It's covered in your textbook, and so I encourage you to look at that equation for the magnetic field along the central axis of the loop, but not in the center of the loop. So here it is. The magnetic field, for example here, that axis is the x-axis. The magnetic field along that axis, v sub x, is going to be mu naught IA squared over 2 times a squared plus x squared to the 3/2. Now here, a is the radius of our current loop, okay? And x is the distance from the center of the current loop to the point P, which is the point where we're trying to find the magnetic field, the point in question, okay? Mu naught's the permeability of free space, 4 pi times 10 to the minus 7 in SI units, and I is the current in the loop. So this is the magnetic field at some distance. Now, if we're only looking along that axis, then the y and the z components are 0, okay? So we're just looking at the magnetic field along the axis here. So let's now think about what this magnetic field would be like if we're far from the center of the loop, where x is a lot larger than the radius of the loop, a, okay? So if we're on the x-axis, far from the center of the loop, under those conditions, this mu naught IA squared over 2a squared plus x squared to the 3/2, I hat is the direction that that magnetic field points along the x-axis, you could say that since x is a lot greater than a, then when you square it, it'll be much, much greater than a, and so you can ignore x squared in favor of, or you can ignore a squared in favor of x squared. So that makes this magnetic field approximately equal to mu naught I a squared over 2x squared to the 3/2 power in the I hat. Now, x squared to the 3/2 power, so first take the square root, that makes it x, and then cube it, that makes it x cubed. And so what you end up with is mu naught I a squared over 2x cubed in the I hat direction. Okay? Now let's think about this a little bit. Remember, a squared is the radius of the loop squared. So the magnetic dipole moment for a current loop, for a single turn, is the current I times the area vector, A. Now the area vector has the magnitude of the area enclosed by that loop, and it points in the direction that the magnetic moment points according to the right-hand rule. So our magnetic dipole moment for this loop in particular would be mu is equal to I times pi a squared in the I hat. I hat's the direction, pi a squared is the magnitude of the area vector, and of course I is the current. So if I sub that into our equation for the magnetic field, you can see I already have the IA squared, so all I have to do is multiply the top and bottom by pi, and I have it. So I can say that the magnetic field from this current loop along that x-axis is approximately equal to mu naught, the permeability of free space, times the magnetic dipole moment for that loop mu over 2 pi x cubed. Okay? So this is an approximate value for the magnetic field for a magnetic dipole moment along the axis of that dipole. Okay? So we could say that this is the case for a current loop. We could also extend that and say for a magnetic dipole moment in general, this would be a nice description of the field if you're far from the center of the dipole itself. Okay, so we said the magnetic fields from magnets and current loops are very similar. They both have these magnetic dipole moments, so they can both be described adequately by this magnetic field equation. The math is pretty much the same. Now let's imagine that we don't just have one magnet, but we have two magnets, both with their own little magnetic dipole moments. So what happens here? You can consider one magnet to be the source of the field that the other magnet feels. Okay? Just like in this little picture here, let's say that the magnet on the left establishes the field and the magnet on the right has a dipole moment that feels the effects of that field. So we have these equations to help us describe how magnetic dipole moments behave in fields, right? We previously discussed that there's torque, right? Torque is equal to mu cross B. And we also previously discussed that there's a potential energy associated with a magnetic dipole moment being in a magnetic field, right? U is equal to minus mu dot B. We used this explanation previously to explain that the potential energy of a magnetic dipole moment in a field will be minimized when the magnetic dipole moment is rotated to align with the field, and it's highest when it's anti-parallel to the field, or 180 degrees, okay? That's how we previously used it. That's not how we're going to use it today. Today we're going to talk about how you can get a force from a potential energy. Remember, this is from our very first semester of physics, right? The force is minus the gradient of the potential energy. So we're going to take this potential energy equation, U is equal to minus mu dot B, and see what force shakes out of that, okay? So magnet 1 establishes a field, magnet 2 feels the field. Let's ignore off-axis effects for now and just look at the force along the x-axis connecting those two magnets. So U here would be, let's assume that magnet 1 establishes the field, right? And magnet 2 feels the effects. So here U would be minus mu 2 dot B1. All right, so let's take the magnetic field that we found for along the axis of the magnetic dipole. So that would mean that minus mu 2 dot B1 would be minus mu 2 times mu naught mu 1 over 2 pi x cubed cosine theta. So here, the cosine theta is from that dot product, and it's how well those two things align with one another, okay? Now, this is our potential energy. The force would be minus the gradient of the potential energy. The x component of that gradient, f sub x, would be minus d dx of U. So here we go, minus d dx of minus mu2 times mu naught mu1 over 2 pi x cubed cosine of theta. All right. Now, the negative signs cancel one another out here, and then I'm just taking the derivative with respect to x of 1 over x cubed. Everything else is a constant. Okay, so that would give me minus 3x to the fourth if I take that derivative. So what I would end up with is the force in the x direction would be minus 3 mu naught mu1 mu2 over 2 pi x to the fourth times cosine of theta. Okay, now that's a lot of mu's, but just remember that mu naught is the permeability of free space, and mu1 and mu2 are the dipole moments of these two things, which we're going to assume to be constants. Okay, so this force here will be attractive, negative, if the dipole moments are aligned with one another. In other words, if cosine theta is cosine of 0, which is 1. They'll be repulsive if the angle is 180 degrees, if they're anti-parallel. So that's where the source of the attraction versus the repulsion between these two magnets comes from. That's the source of that force, okay? And it's a decent approximation to help explain the attraction or repulsion of magnets from one another, okay? Now, of course, the math gets a lot more complicated than this. There's off-axis effects. There's all kinds of things. But I don't think we need to delve that deeply in order for you to understand where the force comes from. All right, now one of the things that we really harp on is whether or not something does work or not. Remember that if something does work, then it causes a change in the kinetic energy. And we previously said from the Lorentz force law that F is equal to QV cross B. And since it's a cross product, it only changes the direction of the velocity, right? And the force is always going to be at 90 degrees to the field in the current direction. So you'd be forgiven for being confused about whether or not magnetic fields do work, okay? Now it's true that according to the Lorentz force law, F is equal to QV cross B, that force does no work on isolated charges. But as we've just seen, okay, there can be an attractive or repulsive force from magnetic dipoles working on one another, okay? If you bring a magnet close to another magnet, then that will cause one magnet, if it's free to move, to slide and be attracted or be repulsed and push away. That does change the kinetic energy. You can also see that if you bring a compass needle in the presence of an external magnetic field, that it will rotate. It will change its kinetic energy as it rotates, its rotational kinetic energy. And so what I'm going to tell you is magnetic fields can exert forces on magnetic dipoles via a different equation, right, than QV cross B. And that causes them to change their kinetic energy, okay? And maybe we shouldn't worry about this as much as we do anyway, because after all, as we've seen in a previous lecture, all you have to do to turn a magnetic field into an electric field is shift to another reference frame anyway. So, meh. Okay. All right. I hope you enjoyed that, and I'll see you in class.